Is there a monitor in the next room over or something?
Okay, let's get started. Good morning. Welcome to E141. Couple announcements for today. Discussions and labs will start next week. Discussions on Monday, and the labs, we have 4 lab sessions. So hopefully everyone will have enough space to do the labs. And very important, you must show up in one of the lab sessions next week. If you don't show up, we will treat that you're not interested in the class, you'll be automatically dropped. So please show up in the lab sessions unless you have a valid reason, in which case you have to let me know that you are still in the class. Homework 1 is due today, and homework 2 has been already posted on the website. It's due next week. And finally, this is your schedule. We finalized the schedule. You have 1 extra lab session here on Friday, and you have other 3 lab sessions as we had originally scheduled, Monday, Tuesday, Thursday, and we have another lab TA, Louis Alarcon, who will be helping you on Tuesdays and Thursdays. So it's very important that you show up during these times, because for class of this size, it's really hard for TAs to answer all the questions. So they are really available to you during this 3-hour period of time to answer all your questions. If you try to skip the lab or not show up, decide to do your own, you are really on your own. So this is the time where you can get help from TAs. And discussions will cover the identical material. They start next week. We'll be talking about some lecture material in more detail, and also give you some hints on your homework assignments, and answer the questions you may have about your homeworks. So I think with this, we're all set with the schedule. Okay. So last time we talked about CMOS manufacturing process, and also some design rules that you need to know to be able to transfer your designs into real-world implementations. So today we're going to finish up with the design rules and start this course from the ground up again. So we will start with the basic device physics and build from there for the rest of the course, going into higher layers of abstraction and to more complicated structure. So we will talk about basic MOS transistor operation and some models for your analysis as a circuit designer. We're not going to go too much into details of device physics, just enough to be able to derive models that are interesting from the design perspective. So this is the bread and butter of today's CMOS processes, MOS transistor, and this is what we've discussed last time, and so a video in much more detail that talked about manufacturing process. So you have basically a transistor consisting of this polysilicon gate on top. You have source and drain regions, and then you have p-type substrate. That's the body of the transistor, and you have isolation for the field oxide. So now the question is, for you as a designer, what do you need to know in order to be able to fabricate this device such that you can create a set of masks that will be transferred over to the real silicon material? And that's what we explained with these design rules that we started last time. So design rule is basically a contract between your process engineer and yourself, your design engineer. And these are guidelines for constructing process masks. So there is a couple of things that you really need to know to be able to design layout, and that is what process parameters do you have in terms of what layers do you have and that you can work with, and also spacing rules between these layers. So it's first important to understand the palette. And in pretty much any process, there is a couple of fundamental layers that I would like to emphasize here, and then we'll talk about the layers that will be available to you in your quarter-micron CMOS process. So as we saw last time, in order to make a transistor, first thing you need to have is well. So you have to have a body for that transistor in which you then implant your source and drain regions. So this well, it can be p-type for NMOS transistors or n-type for PMOS transistors. And it's represented with this color, yellow color here for this layer in this example. And then you have active areas. These are the areas that define your source and drain regions for your transistors. You have NMOS, you have N+, for the PMOS, you have P+. And in most cases, this is represented as a green rectangle. So that's how you define your area. You draw a box that's filled with the green color, and that's your active area. That's where your transistor is. And then you have also another layer, because you have fourth terminal. You have your body of your transistor, and that has to be connected also. And in most cases, it's connected to the source, but you have definitely access to that fourth terminal. And in order to connect that terminal, you basically have to invert your diffusion. So if you have N well, you have to make a connection to that well through N+ layer. And that's called this select layer. So you have, for the NMOS, you have P+, because you have a P well, and for the PMOS, you have N+, that connects your well terminal. And these are normally connected to supply and ground. And then you have another terminal for your transistor that is polysilicon, that sits on top, that defines your gate of your device. And then from there, you have interconnect infrastructure. You have number of metal layers in different processes, more and more as technologies advance, and those serve to connect your devices into a circuit that you designed. So you have metal 1 that connects to your source and drain regions, and then you have higher metal layers that you need to kind of escape over to be able to connect more complicated structures. And as we saw in the previous class, these look pretty complicated. You have metals running on top of each other, and then you have these vias. So it's kind of pretty complicated structure. So you should try to do as much as possible in one metal layer before you really need to escape to higher metal layers, because that's where you have your circuit optimized for speed. You minimize your parasitic resistance and other parasitic effects. And then in order to create connections between these different layers, you have these black boxes that you have basically interconnection between your metal and poly and diffusion. That's represented with these black boxes. So you basically have overlay of two materials, and then you have a hole that is filled with metal layer that kind of connects the two. So these are the layers, basically. That's the basic philosophy. As a designer, to do the layout, you have to assign each polygon to a certain layer that has some meaning in physical implementation. And then overlaying these polygons, you create your circuits. So these are the layers that you will have in our quarter micron process. So this is a 5 metal layer process. Normally, that's the way you specify your process. You say it's a quarter micron, 5 metal layer, number of metal layers, or 90 nanometer, 7 metal layer, and so on. It's an end-well process, and so you have these different layers here for P-well contact, N-well contact that automatically actually includes this select layer and just basically puts appropriate N plus or P plus to create a well contact. And then you have vias basically between all these metal layers. So you have via 1, 2 between metal 1 and 2, via 2, 3 between metal 2 and 3, and so on. So in this class and in your projects, if you do some of the layout, you will probably need to use only metal 1, 2, eventually metal 3. That will be the level of complexity of your designs. We're not going to do microprocessor design to utilize all the metal layers and have really complicated structures. So just to get you an idea of what is possible to do. And then we have active area. We have N diffusion and P diffusion for N FETs and P FETs. And also there is these two layers that actually you can automatically create a transistor that you can basically overlay of your poly, and the diffusion is treated as a transistor. So you can automatically put your transistor down with this N FET and P FET layers. And then you have these select layers for your contacts. Okay, so now once you understand what layers are available to you, then you can do various things and create your circuits. But it's very important that you understand the design rules that are provided to you by technology. And we primarily differentiate between two types of design rules. You have intra-design rules that are basically widths and spacings of objects on the same layer. And then you have more complicated rules that are interlayer rules that basically specify enclosures and overlaps. And these can be classified into three main categories. So you have transistor rules, the way you build your transistors. Then you have contact and via rules, and well and substrate contacts. And also corresponding spacing rules that relate positions of these objects relative to the other layers in the layout. And in deep submicron processes, you have special rules like antenna protection at your gate, and some special density rules to make sure that once you look at your layout, that you have enough density for stability purposes. And if you don't have enough density, today's processes normally have automatic filler insertion, that you have basically a dummy fill that's mostly done by inserting decoupling capacitors for supply lines, but also you can add other dummy structures for other metal layers from metal 1 all the way up to the highest layer you use. So interlayer design rules specify widths and spacings of objects on the same layer. And for example, you will find that the minimum width of your polysilicon will be 0.24 micron. That's represented here as 2. That's basically your lambda, 2 lambda. That is, for this process, 0.12 is lambda. So that defines your minimum channel length. You will have 0.24 is your minimum channel length. The active has a minimum width of 3 lambda, so that will give you your minimum channel width of 0.3 microns. So we are not complying exactly to these lambda rules, so it's not 0.36, but it's 0.3, because for the reasons we discussed last time, that these lambda rules are kind of conservative, and people use more often these absolute rules in terms of standard unit size. And you have also your contact or via hole spacing, and these rules are really related to the capability of your technology. What is the resolution of your patterning mask that you can safely transfer over to your silicon? So in order to do anything useful, you need to put a lot of these layers together, and that's where these interlayer rules matter. So as we mentioned, the most important rule is transistor rules first. So transistor is formed by the overlay of active, polygon, and polysilicon. So this is your transistor over here in this region. That's the overlap of, this is underneath is the channel, and you have source and drain regions over here. So as you can see, these interlayer rules define things like minimum spacing from your active region to your well boundary. Then they also specify overlap of your polysilicon over your active area, and also the distance between, minimum distance between the two, and so on. So now, once you understand these rules, then you go into more complicated ones that relate to vias and contacts. So basically, contact is an interconnection between your metal lines and your poly or your diffusion regions, and vias serve to connect different metal layers. So basically, to create a contact, let's say that I have let's go over here to the overhead. So let's say I have a poly, and this is my minimum width of 0.24 micron. So in order to create a good contact, you have to have some enclosure over that via hole. And then you have a rule for that as well that translates into minimum size contact in this technology to be 0.44 micron. So you be aware that contact, you see that the contact is basically bigger than your minimum size transistor. So for that reason, you really need to use contacts carefully and try to do everything in one metal layers as much as you can before you escape to higher metal layers. And then I have my metal 1 that connects to this poly, and then I again have my metal 1 in blue here, and then I have my metal 1 line. And then in between I have this via hole that's filled with metal and connects the two. So that's the basic concept. That's what you're going to be doing in your layout exercises in the lab. Okay, going back to slides. Thank you. So that's very important object to understand. How do you create contacts in layout? And also these rules specify, in addition to enclosures and minimum size of these objects, they also specify relative distance between the contacts, and also position and distance of these contacts relative to other materials such as polysilicon in this illustration here. And also finally we have our substrates that we need to connect. As I mentioned, that is done through this select layer, that you have basically a well. And if this is, for example, an N well, and this is your PMOS, you have P diffusion here with the select layer. It simply inverts the diffusion and provides N plus area that connects to the well. And it's very important when you do your layout, you will see if you have enough space, put as many well contacts as you can, because you want to make sure that you have a low resistive path between your bulk and supply or ground lines. Otherwise, you will have, if you have high resistive path, then you are inviting a lot of unnecessary parasitic effects that can have detrimental effects to your circuit operation, such as latch up in the worst case, and so on. So just be generous on well contacts. That's a guideline. And here is an example of a CMOS inverter layout. As we said before, that we are going to learn most of the basic concepts on an inverter example and build from there. So shown here is a CMOS inverter that implemented in N-well technology. So this is your PMOS over here. And you have NMOS. So you have a ground. As you can see, you have well contacts here. And the way this is done is you have poly for the gate, and you have common output that connects the two drains. So if you look at the cross section along this AA prime line over here, then you can identify your PMOS and your NMOS. And the way this transistor is built is that you have P plus implant for your PMOS transistor source and drain regions, and then you use this select layer to invert the diffusion here to be able to connect the contact of a PMOS device, and at the same time you create source and drain regions for your NMOS device. And then you have the full structure. And then NMOS has its own P plus to contact with the P substrate. Okay, any questions? Yes.
You mentioned to have as many contacts as possible. Why don't you just like make the contact go continuously through? That way it's wider and even less resistive.
The question is, why don't you make a really wide contact that is less resistive? And that has to do, I think, with the mechanical. You normally don't do that. That has to do with, I think, mechanical stability of your structure. You don't want to have too big of a hole in your metal. But when you go pop up to higher metal layers, you will observe that your minimum size for a contact will get larger because your metal lines get thicker, and then you have to use bigger contacts to connect them. Okay. This is a snapshot of a layout editor that we are not going to use. This has been used traditionally, but it's simple enough and it's illustrative how you create your transistors. You have your polylines, you have diffusion in green, and then you have your source and drain contacts with metal one. And you use 3 contacts instead of 1 big contact over here. You are going to be using a cadence tool because it's an industry standard and it's very good investment to spend some extra time to learn this tool because that's what you're going to be using later on in your career. And this is a snapshot of a 2-input NAND gate in cadence. This is going to be one of your labs, I think lab number 2 or 3, I don't remember, software labs. But you can see basically ground and VDD lines in metal 2 over here. Then you have metal 1 for the local interconnect. You have 2 inputs, 1 and 2, and then you have output of your gate. You're going to do more of this. So now it's very important that when you do your layout, that you also satisfy these design rules. And for that purpose, these EDA tools have very powerful and efficient design rule checkers, design rule check engines. So they basically, what they do is they take your layout as an input, and they also have they can read a technology file. And technology file specifies all the rules that we talked about. So basically all the spacing rules and so on. And then once you give it a topology, then it kind of applies those rules onto your layout and pops up messages with errors that you need to eventually fix. Most of these tools have a so-called online DRC that you can basically automatically check DRC on the fly as you do your layout, so that you can fix them incrementally instead of waiting to complete a couple months worth of work and then fix millions of errors. And this is type of messages you get. This was a MicroMagic. It will look a little bit different in your cadence. So it's basically when you have a violation, you will get a warning that there is not sufficient spacing in this example between poly and active area. And what's also important is that most of these design rule check engines implement so-called hierarchical design rule check, because for the complexity of designs that we talked about in last week, you have millions and millions of transistors, but luckily they are hierarchical in a sense that you repeat one cell all over the place number of times. So you only need to do is basically do the DRC check once on that cell and make sure that all of its instances then are also valid. And then, of course, you need to check for the interconnections between all the cells, but that's simpler than doing the entire flat DRC check. And since these layout drawings can be really complicated, it is often a very good idea to simplify, at least in the conceptual phase, the way your circuit topology is going to look like. And for that reason, people have developed this theory of sticks diagram. So this is basically dimensionless layout drawing. And only topology is important. So you just basically define the relative spacing, not spacing, but relative uh, position of your objects relative to each other. So you have, for example, you have horizontal diffusion for the PMOS, horizontal diffusion for the NMOS, give it a relative size with these numbers here, and define the connections. And then there is a bunch of tools that can basically take automatically this sticks diagram and also know the design rules, and then can provide compactions to knowing the design rules, it can translate this into your real layout. But the problem with that is that oftentimes you don't get really what you want, because the tool decides to position transistors and contacts the way it understands that diagram, and sometimes you don't have really the highest density layout, and you would want to eventually do some manual intervention in the layout design. But oftentimes it's a good starting point, and then you can modify your layout from there. But hand crafted design is still the most valuable. Okay, so that's what you're going to be doing in your labs. Any questions about this material? All right, good. So now we are going into MOS transistor, and we will define basic operation, modes of operation, and define relationships, IV characteristics of deep submicron MOS. So most of you have taken 105 and 130, and this material is familiar to you. You've seen this a number of times before, so I'm not going to go too much into detail of device physics, but we will just go into sufficient detail to be able to extract useful models that we are going to use as circuit designers. So the simplest model of a MOS transistor is a switch. You can treat your transistor simply as voltage controlled switch. If you have, for example, NMOS here, when your gate to source voltage exceeds certain value that we call threshold, then your switch is closed, and your transistor behaves as equivalent resistance between source and drain, between the conductive electrodes of your device. And when VGS is less than VT, your switch is off. Simple as that. So that's a switch model. You have VGS less than VT, the switch is open. VGS greater than VT, you have equivalent resistance between source and drain. For NMOS transistor, all your voltages are positive, and in the PMOS case, you have to invert the polarity. And this inverting bubble reminds you that this device is active at logic 0. So when you apply logic 1, then you have this switch turned on. When you apply logic 0, then you have your switch turned on over here. So they're complementary devices. These are the types of MOS transistors that you will find in literature. Most commonly used is the NMOS enhancement mode. That's the device that we are going to analyze in this class, and that's basically a device that turns on at certain value of the gate voltage that enhances conduction in the channel. There is also this depletion region device that is basically conductive when you don't have any voltage applied across your gate and source terminals, and you have to apply negative voltage in that case to turn it off. This is a rather ancient device. It's been popular in 70s and 80s with the NMOS logic as active load for circuits, but it's almost non-existent in today's technologies. And then you also have the PMOS symbol that has this inversion bubble. It's complementary, works at the complementary logic levels. And then you also have this schematic representation of your transistor as a 4-terminal contact. Normally your bulk is connected to source, but in some cases you want to do maybe you want to have a bias on your body, and this is typically used in analog design more often than in digital, although there is also techniques for body bias in digital design. Sometimes if you want to, for example, put your transistor in a sleep mode, you want to avoid leakage, then you want to do reverse body bias and so on. You can even do forward body bias to improve the speed and various techniques. So that's important to know as well. So these are kind of devices that we'll be working with. Okay, now that brings us to basic operation of MOS transistor. So let's take a look at NMOS device here. So we can identify N plus source and drain regions, P substrate, and also gate electrode, polysilicon gate with thin oxide between the two. So the thickness of this oxide is it's in tens of nanometers range in this technology that we're going to be using in the class. So when you have initial case where all your electrodes are at ground, zero potential. So what you have in that case, you have depletion region between your PN junctions that are formed between drain and substrate and source and substrate. And your transistor is turned off. So now let's assume that we apply a little bit of positive voltage on your gate. What this does is it basically creates a capacitor between your gate and the channel. And for very small values of this gate to source voltage, you have positive carriers attracted at top of your gate oxide on the gate terminal, and then you have negative charge underneath your gate in the channel region. And first, this negative charge is actually built by repelling holes from this region, and you have immobile acceptor ions sitting here. And then when you keep increasing your gate to source voltage, you will soon reach some critical value that we call threshold voltage, where you basically invert the region of the channel. And instead of P material, you have basically N carriers under the channel. And then you can apply drain to source voltage to have these carriers move between drain and source, and you have a current conduction. So that's basically all you need to do to know at E141 level for device operation. And as you remember from your device class, you have your basic threshold voltage defined as VT naught, where you have no bias at your bulk terminal, and then you have this correction term for body bias. So this is a body effect factor gamma here that describes the impact of biasing your body terminal relative to the source on your threshold voltage. So basically, it's a very simple structure. You have a gate that controls the amount of charge that can be attracted underneath the channel for conducting purposes, and then you have source and drain that control the flow of the charge, and also you have this body terminal that basically just modulates the characteristics of your transistor in a sense that it shifts this threshold voltage where you have your conductivity. So you have your threshold voltage is related to oxide thickness and device parameters that are captured with this Fermi potential that you have KT on Q times Ln doping concentration divided by this Ni. And this 2 times the Fermi potential is about negative 0.6 volts for P-type substrate. Gamma is the body factor, and VT naught is approximately 0.45 volts for this quarter-micron CMOS process that we'll use in the class. So what this relationship tells you is, let's assume that you have NMOS device. If you apply body bias, then your threshold may increase or decrease depending if you do a forward body bias or reverse body bias. And that's illustrated over here, the body effect business. You have your threshold voltage, and then you have bulk to source terminal. If you go into negative direction and decrease the voltage of your bulk relative to the source, then your threshold voltage increases as described in that previous relationship that we had, and that's a reverse body bias. You can see that you can, starting from 0.45, you can increase your threshold by quite a bit. Going into another direction has a restriction because you can't really do much of a forward body bias on an NMOS because you have P substrate and you have N plus regions for source and drain, and therefore you have a diode. It's a PN junction over there. And if you go too much in a forward direction, you basically no longer have your transistor. You just have a diode between your bulk and the source region. Okay, good. So now we'll do a simplified derivation of the drain current using the concepts that we introduced so far. So basically, when you apply gate voltage at the gate electrode, then you have charge in the channel that is controlled by that gate voltage. And if you draw over to the overhead here, if you draw the cross section of your device, so this is your oxide, this is your gate, so we have this depletion region around here, and then we have gate to source voltage. So now the amount of charge that you find accumulated under the channel at some point x, if we introduce this as an x-axis with origin over here, and if you look at some point over here x, so then you have potential over here, it's V of x. So the amount of charge, because this is a negative charge, will be minus C ox. So it's a unit capacitance per unit area. And assuming that you have exceeded your threshold voltage, then you have VGS minus Vx. That is this channel voltage. It's greater than the threshold, where this parameter C ox is equal to epsilon ox divided by oxide thickness. So now your drain current, and the drain current is over here, is proportional to this accumulated charge. It's also proportional to the velocity of the accumulated charge, and it's also proportional to the width of your transistor. The wider the channel you have the more charge that travels across. And this velocity parameter here is given by simply as mobility and electric field, dV over dx. That's minus mobility times electric field across this at this point x, and you have electric field going from drain to source, so you have a minus sign over here. Okay, so now going back to slides. So when you combine this velocity and charge and integrate over the channel, you end up with this simple current voltage relationship for your device. And over here we recognize this parameter Kn prime that is the transconductance of your device. It's a mu times Cox, so it's a mu epsilon divided by Tox. And you can see that when you have a very short channel, then you have high current, which means speed. And analog designers do a lot of interesting things with channel length, but in digital gates, in majority of cases, we will use only minimum channel length, because that device gives us minimum gate capacitance and also gives us a lot of current, because you're interested in speed and compaction. Okay, and so the more gate to source overdrive, you apply the higher the current. And so now let's analyze modes of operation now that we understand the principle of MOSFET basic operation. So we have basically two modes that we really care about. So this is linear mode or resistive mode and saturation mode. So for this linear mode, the gate to source voltage has to be greater than VDS plus VT. This also implies that your transistor is turned on because VDS is positive in this case for the NMOS, so you have VGS is greater than VT. So you have overdrive over your on the VGS you have VGS minus VT, which is your VGT, that's the overdrive over the threshold voltage. And then you have fairly small VDS that's less than VGS minus VT. And in this case, you basically have a conductive channel between your source and drain, and you have linear relationship between your drain source voltage and your current. So this is really like transistor can be analyzed as a resistor. So going to the overhead here, so you basically have VDS and ID, and then you have this linear mode. Your current increases proportionally to the voltage applied across drain and source. So now if we keep increasing this drain and source voltage, then what's going to happen is we are going to enter a saturation region where you basically can no longer assume that the potential across your channel, so if you have your gate and source, so drain, so you can no longer assume that you have your channel potential here VGS minus VT. That's your V of X if you go from on this direction X, and this is 0, and this is some point X. So when you keep increasing this drain voltage, you will soon have that your VDS is greater than VGS minus VT. And what's going to happen in that case, your channel will be pinched off, and you will basically have reduced effective channel length across your channel. And then when you keep increasing and increasing with this VDS, then the depletion region on this side is going to be increasing, and you basically can no longer increase your current. You will be saturated through this pinch-off mechanism. And this means that your current at some point will reach a constant value and can no longer increase. And this occurs at VDS is equal to VGS minus VT. But in reality, this is not quite true that you can model your transistor as an ideal current source. What's going on over here is that you basically have what's called channel length modulation. If you keep increasing your drain to source voltage, then you basically have that the effect that your effective channel length reduces, and what matters for your current expression is not the drawn WNL, but rather the effective WNL, because that's what really gives you electrical properties for your device. And this can be actually then corrected in a following way. So you basically have increase in current with the increased VDS, and this is attributed to a factor that can be modeled simply as 1 plus lambda VDS, where lambda is channel length modulation parameter. So going back to slides, please. So for this condition, you have drain current that saturates. And then you have this quadratic dependence between drain current and VGS minus VT. And including channel length modulation, then you have this correction factor that gives you a slope in the saturation region. Okay. So these are the modes of operation of your transistor. We started with no bias, where we had no current as well. So that was transistor in a cutoff when VGS is less than the threshold. And then you have ID is equal to 0. And then we have resistive or linear mode of operation, where VGS is greater than VDS plus VT. And then we have this linear dependence IV characteristic, where your transistor can be modeled as simple linear resistor. And in this case, mostly VDS is small, so this term can be neglected, and you have really a linear relationship in VDS. It's a second order term. And then you have the saturation region, in which case you have quadratic dependence. So now this is IV characteristic for a good old MOS transistor, because these relationships are really old. That's maybe a transistor 15 years ago that exhibits this quadratic relationship. And so on this characteristic, you can see for a family of curves corresponding to different VGS values, we have higher and higher current, and this is a SPICE simulated curve. And then we can distinguish between this resistive and saturation mode that is separated by this VDS is equal VGS minus VT line over here. So if you're on the left, you have almost linear relationship. If you're on the right, you have ideal voltage source to a first approximation. And as you can see, if you keep increasing your VGS, then you have then the spacing of these curves for equal spacing in VGS kind of gets larger and larger on the y-axis. And this is due to this quadratic dependence on ID versus VGS characteristic. So if you know all of this, then you can simply model. One of the ways you can model your transistor is through this model that represents a transistor as a current source. So in a linear region, you have this expression over here, and in saturation, you have this quadratic dependence with channel length modulation, where you define your threshold as given in this equation. So you really need a couple parameters from the technology. You need this threshold, you need this gamma, lambda parameter, and you need the parameter of this transconductance for that's a property of your oxide and your gate material. And in discussions and homeworks, you will have the opportunity to play with these parameters and kind of understand better where they come from. So now if you know all of this, that's good, and but forget it. It's no longer valid, okay? So what we are going to do is really analyze this deep submicron transistor that behaves quite different from the well-known good old quadratic MOS transistor. So most importantly, there is a couple differences, but most importantly, you have this linear relationship between the current and gate to source voltage. And your saturation occurs much sooner in your transistor in deep submicron than you had on this graph for transistor that is not deep submicron. It's basically channel lengths greater than quarter micron. So we are kind of at the boundary, but we will still treat our devices deep submicron. So you enter this early saturation region. So what's going on here is that basically once you have your channel that is shorter and shorter, and you keep applying large electric field over that channel, then eventually you will hit the limit, and your carriers will be velocity saturated. So that's the most important phenomenon that we need to understand for these deep submicron transistors. and that is this velocity saturation. So the velocity of carriers saturates due to this carrier scattering effects, then run into each other and then just cannot go faster. So if you plot a velocity of your carrier, and on the vertical axis and on the horizontal axis you have applied electric field, then for small electric fields you have constant slope. So it's basically constant mobility of your carrier. So your velocity increases as you increase the field. And if you keep increasing the field, then you basically end up with this scattering effect, and you have constant velocity. And for both PMOS and NMOS, this constant is approximately equal to 10 to the 5 meters per second. So it's 10 kilometers per second velocity of your carriers. And the value of this electric field at which these scattering effects dominate and you model your velocity as constant is called critical electric field. That's obviously property of your material, and for the NMOS, this is about 1 to 5 volts per micrometer. So we assume that we have quarter micron technology, and then we have this electric field, critical electric field of 2 volts per micron. If you have quarter micron channel, you have your velocity saturation occurring at 0.5 volts. You have a question?
As the minimum feature size of the transistor is being scaled down, the supply voltage is also being scaled down. So why isn't it a constant field scaling? Means why is the field increasing?
Because that's a good question. The minimum feature size has scaled down, the voltage has scaled down. So basically the voltage has been scaling down at a slightly reduced rate than it was in the past. So basically we have the feature size has been scaling at a faster rate, such that when you apply a voltage over your drain and source terminals, then you have excessive electric field. And also you have basically this channel length modulation effects that your actually effective channel is shorter than your drawn channel, which actually increases the field over the channel, the effective channel, and for that reason you have this velocity saturation effect. So okay, the main difference between a long channel device and a short channel device is this velocity saturation effect that basically tells you that this flattened out region of ID versus VDS curve occurs much sooner in your short channel devices than in the long channel devices. So you have a very narrow bin of resistive mode of operation for short channel, and then you have this extended saturation region compared to the long channel device, which behaves as a resistor, and then you have the long channel device saturation mode after that. And this VD sat occurs much sooner than the actual saturation for long channel device. So if you plot ID versus VGS, then you can see that they both start in a quadratic fashion initially, and then you have linear dependence for short channel, and then you have this quadratic dependence for the long channel. That's the main difference due to this velocity saturation effect. So now regions of operation. So let's assume that we have in the same technology, in our quarter micron CMOS, that we have W over L equal to 1.5. So you have the same gain for the current in your device. And then we analyze two cases. One is long channel device that has this quadratic behavior, and another is short channel that has a quarter micron channel length. So as we saw in the previous case, we had a clear boundary between resistive and saturation region defined by this VGS minus VT. So what happens in the short channel device, we basically have this velocity saturation mode that occurs much sooner than where would saturation occur in a long channel device model. And now let's see how we can model this phenomenon such that it's captured in the design equations that are important to us as circuit designers. So two things. You have velocity saturation that occurs much sooner than when regular saturation would have occurred, and you have also linear instead of quadratic relationship with gate to source voltage for that reason. So to include velocity saturation, we can approximate that velocity versus electrical field relationship using this expression, mu times electric field divided by 1 plus electric field divided by this critical field, and it's equal to this constant value Vsat for electric fields higher than critical. Now, for the continuity of this equation, you have to have that Vsat is equal to also holds in this expression, and from there you can calculate the value of Vsat and critical electric field. So what does this mean for the current equation is that your gain factor is now modulated with this velocity saturation term. So this is called, so you basically had your old expression going to the overhead, please. So you had that your ID for velocity saturated short channel is equal to this K of VDS times ID for your long channel device, where this K of VDS is equal to 1 over 1 plus VDS times this critical field times L. Okay. Going back to the overhead, please, so can I copy down the... So now we can compute this value of VDSat by writing down the equations that IDSat is equal to this velocity saturation times Cox times W times VGT minus VDSat, where this VGT is equal to VGS minus VT. And we also know that this IDSat is equal to K times K of VDSat times mu Cox W over L VGT times VDSat minus VDSat squared over 2. And then we figure that this VDSat from here, by making these two equal, is equal to this K of VGT times VGT. So we see from this expression that for the short channel effect, and this VGT was basically the boundary where saturation point, for the saturation point in your long channel transistor. So you can see from this expression, plugging it over here, that for a very short channel transistor, this value is much less than 1, which tells you that the velocity saturation, it's another way of saying that velocity saturation occurs before the saturation in conventional devices. That's the important point to remember. Okay, so going back to slides, please. Thank you. So in this deep submicron, there is really 4 regions of operation. You have cutoff, you have resistive, then you have this saturation, and you have also velocity saturation. And in order to develop models for hand analysis, we need to, it's good to have some simplistic assumptions so that we can get a handle on equations. All of these like second order effects are modeled in your SPICE model files, but if you try to just include them all, the equations will blow up in your face and you're stuck. You can be spending the rest of the semester just solving a simple CMOS inverter, and we're not going to do that. So for that reason, we need to do some simplifications here. So let's assume that first simplification is that this velocity saturation boundary here is basically occurring for all of the VGS points at the same VDS. So we have just a straight line over here for the short channel effect. And that's how we define these regions of operation. So if we define VGT is equal to VGS minus VT, and we simplify this VD sat simply as the product of your effective channel length and the electrical field, because that's the onset of velocity saturation, then we can basically provide this simple model where we identify linear mode over here. Then we have velocity saturation that occurs early. And then we have also for small value of VGS, we have a classical saturation region. As you see, this boundary is still this quadratic boundary from the good old quadratic CMOS. So you have basically this boundary defined by VDS is equal to VGT. That's the boundary between linear and saturation. And when your gate to source voltage exceeds this VD sat, then we have velocity saturation. That's a pretty simple model. So now, we have a linear relationship for the velocity saturated device. So now, as I said, it's a good to have to know where all these effects come from, but ultimately what you would want to have as a designer is a really simple model for hand analysis. And this effect of velocity saturation can be modeled in various ways. People sometimes use alpha power law model for the drain current, that basically you have this, instead of quadratic relationship, instead you say this exponent is no longer 2, but it is some factor that is between 1 and 2, and that includes that velocity saturation effect. This is one of the models that this is the model that we are going to use in the class for MOS transistor. So it's very nice that you have all these 4 different modes of operation. You have only one formula. So that's a unified model. If you define this VGT is equal to VGS minus VT, then for VGT is less than 0, your transistor is cut off. So you have ID is equal to 0. For VGT is greater than 0, you define this Vmin. That's the minimum between your VGT, VDS, and VDSat. And depending on which of these 3 voltages that you need to calculate ends up being your choice, when you plug it back in here, you have basically, if Vmin is equal to, let's say, VGT, you have your good old saturation mode quadratic MOS. If you plug in VDSat, you have your velocity saturated device. If you plug in your VDS, then you have linear region. So it's kind of nicely calculates I versus V relationship for all possible regions of operation using these simple definitions. And you have also this channel length modulation effect over here. Now the question is, okay, this is just a simplified model, how accurate it is. And you can calibrate that using SPICE, where you basically have blue lines are the model over here, and these circles are a result of SPICE simulation. And of course, there is some discrepancy between the 2 results, but what's really important is that this model is valid in regions of operations that we really care about. So what we care about in analyzing MOSFET transistors found in digital gates is this region over here, where you have large VDS or in this linear region when you have basically pretty good agreement between the spice and the model. For this region, it's a kind of transition region. We never want to, we don't do analog circuits here, so we are never really interested to see VDS is equal to 0.8 volts. We want either VDS to be 0 or VDD. And in these corner cases, these models are very good. Okay, any questions? And in your homework, you will have basically the homework that's posted today. You will play more with these parameters and try to better understand the model. So you will have, I think, 4 problems. 2 will deal with extracting these device parameters. And you will also have some problems on noise margins and voltage transfer characteristics. So for the PMOS transistor, you basically just reverse the polarity of the voltages. So for the PMOS, you have gate to source voltage that is negative compared to the NMOS, where because you have PMOS that is turned on at logic 0 and turned off at logic 1. Okay, so in addition to these 4 regions of operations that we defined, cutoff, linear, saturation, velocity saturation, it's very important to also understand this sub-threshold behavior of MOS devices. And that occurs where your gate to source voltage is less than the threshold. So you think, okay, so it's very important and interesting to analyze transistor when it has enough current, when it can perform some interesting switching behavior that defines Boolean functions and provides useful computations. But then you assume that when the gate to source voltage is less than that threshold, your device is completely cut off. But that's been true maybe 10 years ago, but in these days, in modern processes, you have more and more of sub-threshold conduction that is manifested as leakage current. And going to the overhead. And what's even worse is that when you plot your ID versus VGS curve, then you have, and this is the logarithmic scale. And this is your VT. Then what you can see, you have exponential dependence on your ID versus VGS. So this was exponential here, and then you had quadratic, and then you had linear. And now these days, when you keep scaling your threshold, and you have larger designs with millions of transistors, this really becomes to be an important effect. And the way you model this is you can simply model it as I naught times e to the QVGS NKT, when n is defined, and we'll see that more in the upcoming lectures. That depends on this capacitance ratio. So what this tells you is basically that if you keep decreasing your threshold, then you end up in more and more pronounced leakage effect. And the slope of this exponential curve here, this S, is equal to this NKT on Q ln 10. And what this tells you is basically when you calculate, take 2 points on this curve. So basically you have, what's interesting to know is how much in voltage does it take to have a ratio of leakage current equal to 10. And this slope is normally expressed in certain millivolts on the voltage axis for a decade of change in current, so 10x change. And the typical values for this sub-threshold slope are 60 to 100 millivolts. At room temperature, this KT on Q factor is 26 millivolts, and then you need to multiply this by this factor that typically ends up in this range. It's about 90 millivolts per decade. Yes?
What is CD? What is capacitance CD?
That's drain junction capacitance. We'll see that in more detail in the upcoming lectures. But this is really important effect in modern designs, and it's quite scary that you have exponential increase with the scaling of thresholds. Okay, and we'll get back to that in analysis of power consumption. Now going back to slides. So what you really need to know to be able to analyze your MOSFET transistors is a couple parameters that are provided to you by the technology. And in the textbook, you have a table that we'll be using in homeworks and so on this semester of all these parameters that you need to worry about in designing your gates. So you have this threshold voltage for NMOS is 0.43, for PMOS is negative 0.4. Then you have this body effect parameter that modulates your threshold depending on the source to bulk voltage. And you also have this VD-SAT that is slightly higher in the absolute value than for the PMOS than the NMOS. Then you have this K prime, that's your transconductance parameter that figures in your drain current. And then you also have this channel length modulation parameter. So these are really the parameters that you need to understand where they come from and be able to plug them in into current voltage relationships that we defined, and that will get you started in understanding of MOS transistors. We will be using, as we go forward toward more complicated structures, we will abstract out most of these effects and use even simpler models when we analyze gates, because we don't want to worry about every single electron up in at the gate level. So there is a number of transistors models that you can use in your analysis, and one that is quite popular and very commonly used is to model your transistor as a switch. So it's a very simple model, and that aids in calculation of propagation delay in your circuit. Remember the RC network that we talked about in the last lecture? So it's basically you have equivalent resistance that is a model of your transistor. That's the driver. And then you have the capacitance that was the load that is presented by the gate in next stage. So that was the gate capacitance of the next stage. And you can certainly calculate this resistance, equivalent resistance on resistance of your transistor in an exact way. So basically, all you care about is where your switching occurs for the delay analysis, because you want to analyze how long does it take to reach the 50% switching point, and you don't care about the rest. So let's assume that you have, for example, pull down operation, and then you start from VDD and you go all the way down to VDD over 2. So to precisely calculate average resistance, you can simply calculate at each of these points and then average out. But for most analytical purposes, it's sufficient to provide a first order approximation that your equivalent resistance is simply average of the two endpoints. So you have starting point at VDD, and then you have endpoint over here at VDD over 2. So all you need to compute is basically current over voltage ratio for rather voltage over current ratio, and average out these 2 points. And you end up with a simple expression like this, that your equivalent resistance is 3/4 VDD over ID sat 1 minus this term that you can oftentimes neglect to a first order. So this shows equivalent resistance using the analysis that from the previous slide versus voltage for a transistor of W over L ratio of 1 and a channel length of 1/4 micron. It's a minimum channel length, and as I said, that's the channel length that we'll be using mostly in this class. These results are quite different if you want to decide to use longer channel, and it's important just to understand the methodology and the way you can calibrate and calculate your equivalent resistance. So if you are given some other channel length or width, you can pretty much calculate, recompute this curve. But it's important if you assume that the channel length is 1/4 micron, we simply scale the resistance by this W over L ratio. So the wider the channel, the less resistance you have. And you can basically just use these numbers and scale with appropriate W relative to your minimum W given here. And as you see that when you keep decreasing your voltage, you have sharp increase in your equivalent resistance. Where is that coming from? Any guess? Even further down, this region over here. So what happens when you keep decreasing your gate to source voltage? Is that? Sub-threshold, exactly. So your transistor turns off. It no longer acts as a switch, so it's closed. So this is really the what happens here, why it's shooting up. This is, again, you can find this in the textbook, the parameters for this W over L unit size transistor, and you can find equivalent resistance for both NMOS and PMOS at some interesting points on for VDD, so you can check out those numbers. Okay, so much about MOS transistor. Any questions? All right, so I can assume that you know everything about MOS transistor. And now we will start looking into logic gates, moving up in abstraction, and we will analyze first a CMOS inverter. So a CMOS inverter, as you saw this configuration, it's basically PMOS and NMOS transistors connected in this configuration where you have common gate and then you have common drain, and it's loaded with certain load capacitance. And basically it provides inverting operation. When you have 0 at input, logic 0, then it provides logic 1 at the output. Logic 1 at the input is propagated as logic 0 to the output. So it's very simple truth table inverting operation. This is a layout of CMOS inverter. This is what you're going to do in the lab. So you basically have in this N-well process, you put N-well for the PMOS, then you put this diffusion region, then you have a lot of contacts for your well, and this is your drain side here, over here. Then you have NMOS in a similar way down here. You have well contacts, you have your drain, and then you have a gate polysilicon running on top of both devices, and then you have common drain that's your output of a circuit that's in metal 1. So now if you have 2 inverters, it's a good idea to just basically build a layout for one and just put them next to each other. So in order to do so, you basically just keep in mind the interfacing between different circuits. So it's always a good practice, if you can, for example, for this kind of circuit, to put your input and output terminals at the relative vertical position. So when you put these two devices next to each other, all you need to do is put a straight line. So you don't need to jog around. And so you can easily abut cells and connect them to each other. So now going further, this is a model for analysis of inverter using a simple resistive switch model that we talked about for MOS. You have basically a pull-down resistance that is represented as equivalent resistance of NMOS transistor that is pulling down when input is equal to VDD, and you have pull-up resistance that's equivalent PMOS when input is equal to 0 and NMOS is open. So I think I'll just stop here and we'll continue this next time. All right.
I have a question too.
Oh, okay.
Sorry, I don't have time. Actually, I have a question in layout of the MOS transistor. In your example, like the drain and source is not in symmetry. You know, you know. So why is that? Like drain and source is like this, and the gate is there.
Oh, they're kind of off,
Yeah.
misaligned. It's basically just that was for the convenience of connecting the thing to
Oh, really?
the well. Sometimes it happens. It's not uncommon.
Oh, okay. Thank you. That's all.
Yeah.
Can you have a question about like the lab? Because I officially enrolled in the Monday lab. So this coming Monday, should I go to like the Monday lab? Because I want to switch to Friday lab. So
You just show up to one lab that you want to attend and stick
Oh,
to
I
it.
see.
Yeah. So if you want a Friday lab, show up on Friday lab.
I see.
On Friday.
Yeah, thank you.
in one of these that ID versus VDS curve, there is this saturating. You made a comment that we are mostly interested in the part where it's flat current.
Yeah.
But in digital circuits, we are interested more when the input is logic 0 or logic 1.
True.
So that means that my transistor is either in the cutoff state or linear state.
It's in the cutoff or saturation, right?
No, linear.
If it's logic 0 or logic 1, if you have a full swing over the gate, then you're saturating the device.
If I have a full swing on the VGS, then my VGS minus VT is greater than VDS. So
Okay.
I'm in a linear zone.
Yes, that's true.
So either I'm in cutoff or in linear, not in the